All right, so let's get started. Yesterday, we, sorry. So yesterday, we started with the second part of the course, which was databases. We identified that databases, they are since when we first started using computer, we started storing our data on computer. Earlier forms were storing in the form of files in different folders, and then this unstructured data, unorganized data, it was suffering from what is called in uh, the referential integrity. This data won't have any built-in integrity to it, and different files can have different information. Uh, the way this was solved, it was using set theories. Excuse me. The way this was solved, it was using set theory concepts. There are attributes that we'll define. These attributes are going to store different values, and those attributes are related to the domain, such as the size, the length, the distance of pitch, the count that you would want to produce. Multiple combination of these attributes, they together become the primary key or entity identifiers. What we also found out that to there are two types of programming languages. One is declarative and one is prescriptive. We found out that in databases there is a language which is called SQL or SQL, structured query language. And structured query language is English-like sentences that tell the DBMS, the database management system, what data to extract and how to extract that. There are two types of values that we can save, scalar value and non-scalar value. Scalar values can be sorted, non-scalar values, they cannot be sorted, and they should be divided into different columns, separate columns, and stored in their own independent columns. Then we found out the role of DBMS, that DBMS prevents direct access of data by the users. It actually controls and monitors, and every request that comes for the data, it goes through a database management system, and it ensures that the correct access is provided and the files and the referential integrity of these files are maintained. A couple of questions related to installation and setup of your machine. The reason I showed you Docker is because I did not want you to go through a very difficult, time-consuming installation process. If you are not able to get Docker running, that is fine. All you have to do is you have to install SQL Server, like Express Edition. I have shared the link, and SQL Server Management Studio. Using Management Studio, you will be able to run and execute the queries and create databases. And SQL Server is going to be the database technology. If you use Docker, there are commands through which you can avoid the installation altogether using a simple command. If you're not able to get that running, that is also fine. There are there are four types of programming that you can do in SQL. It's called they're called DML, DDL, DCL, and I think it is excuse me. And the fourth is DTL, data transaction language. We saw DML at length yesterday. We saw the select statement. There are multiple type of select statement. We saw the insert statement, like how to insert single value, how to insert multiple value, how to provide how to control the order in which you would want to insert the values. And then we saw update. We saw how to have subqueries inside update and have a collective effect or restore databases. And then we saw a couple of delete statements. Today, we are going to see the DDL or data definition language, which is about creating and altering databases. There are a couple more things that we're going to look at. All right, so with that, let's switch to data control language. All right, so let me pull up the SQL Server Management Studio. And then over here, yesterday, we used the demo database extensively. And then we had at least two tables here. One was the car stock and the second one was people. Let's look at the uh, the definition of these columns. So if you remember our commands from yesterday, we generally start with the use command and then we provided the database name such as DemoDB. And if I hit F5, it is going to switch database here. It's always good practice to have this as your first statement, so you would know that what database you are into. If you want to see the schema of a database, there is a, a command called execute. And then if you give it name of the built-in stored procedure, sp help, it is going to give you the entire schema of all the objects that are there inside this database management system. And then if you notice this, there are a couple of user tables. We are interested in the people table. So if you want more information about this people table, we are going to run another command sp_help. And this time we are going to provide the object name itself and hit F5 again. Right. So notice that there are multiple columns. I directly used this example database yesterday, but then today let's go ahead and create this database. Let's go ahead and create this table. So the command that we are going to use to create this table, let me open up a new query. And this time I'm going to create a new database. Right. So the command that we're going to use is called create table. And then after create table, you can you provide a table name to it. This time I'm not going to call it people, I'm going to call it person. And after this, there are in the parentheses, you are going to have to specify the columns that you would want. So we had first name, last name, and favorite color, and the data type is var char. Now, there are multiple data types available inside SQL Server, and these data types, they indicate uh, what kind of storage you would want to provide. So if I want to create a column called first name, I'm going to put the column name first, followed by the data type. Now I can provide, because first name is going to have multiple characters in it, I can provide it a significant size, and then this size here is going to define or dictate that the number of characters, the maximum number of characters that it's going to save. There are other types as well, like char 50. Uh, the difference between char and varchar is that varchar is more memory efficient. So it is going to keep a provision that there are maximum 50 characters that you can save. But then if you save, say, my name and it is 3 letters, the rest 47 characters, they will not be wasted. So depending on the data that you are storing in this particular column, varchar is going to give you up to 50 spots. Yesterday, we also discussed another keyword called null. And then null keywords are null is a tricky keyword. If you don't want to allow a particular column to have a null value in it, you're going to have to specify that it is not null. You have to explicitly mention this. The reason we would want the first name to not be null is because if you keep scrolling down, you will find out that the primary key for this particular table is last name and first name, right? A primary key cannot be null. And then if you would want that, you will have to store that over here like this, not null. Let's build another column on the same lines, and we're going to put not null here again. And the last column was favorite color, and then it is another varchar, and I'm going to put say 30 characters. But then this column is optional. We are okay with people not specifying their favorite color, and with that, if you want to allow that condition, we'll have to put the null keyword here, and then this becomes an optional column after that. So I'm going to save this. Let's execute this query. Sorry. Let's go ahead and execute this query. And it is saying that command completed successfully and the completion time. Now, if I come here into demo database and refresh it, you're going to notice that there is a new person table created. Now, let's go ahead and run a select query on this. Select star from person. It does not have any data at the moment. It is only going to appear after we run a couple of insert queries, but let's go ahead and defer that for now. Now, probably this is a good point where I can come and run our exec query one more time, exec sp underscore help, and look at the person table closely. Now we see that our three columns are present, but then it is saying that there is no identity column at the moment. And if you look at this particular section here, it is saying that the identity column is still missing, but there are a couple more sections down below which are talking about constraints. Now, a constraint is a condition that we apply on a table or the columns within the table, and then these constraints are for our instructions for the DBMS, the database management system, as to how the validation or operations are to be performed when we are working on these columns. One of the constraints that we would want is that the first name and last name combination should be unique. And then for such unique combination, there is a constraint and it is called primary key. So the way constraints are defined, there are two ways of doing that, but let me show you another way of let me defer that and let me show you how to use another command before this. All right, so we only have three columns. What if we wanted a fourth column in this, which is say favorite food as well? And for that we'll require another command, and it is called alter. So create is going to create a table for you. I should have put capital. Create is going to create a table for you, but then alter table is going to modify an existing table. So in the people table, if I want to add a column and I want to call it favorite food, I'm going to specify another column type or size, and then I'm going to specify a null here. The reason I'm specifying this null is because the table is already created, and hopefully, possibly, there is already some data inside it. You can execute this command at a later point on an existing database, and when you are inserting value, when you are adding a new column to an existing table, you will have to specify, you cannot leave it not null, because this would immediately violate the existing rows in that database or in that table. So you would want to avoid that. You cannot even run that query because it is going to fail right away. It's going to say that there is data and then you cannot have not null constraint here. So you will have to mention null in the beginning at least. After this, you, if I now run this command, I'm hoping that it is going to add a new column. Let's see what happens. So when we ran this, it said the command is successful. Let's go ahead and run the sp help command one more time and see how many columns we have. So we have favorite color. Okay, so I don't want, okay, I added it to the wrong table. I wanted to add it to the person table. So I added the column to the person table, and now if I execute this, you see that there is a fourth column that got added to an existing table with the values that we specified. Now, the reason this command is important is because you would always want to separate out the creation of the table from the constraints that you would want to add that table. Another thing, using alter table, the way we have added a column, we can also remove a column. So let me come down here. I'm going to use the same template, and instead of add, I'm going to say remove, and it is okay. I'm forgetting. I think it is delete column. Ah, okay. Let me look up this word real quick. Okay, so it is not remove or delete, it is drop column. Then I cannot specify this. When I do this, it is hopefully going to remove column that we just added. Okay, so favorite food is gone. Let's go ahead and add that back again. And favorite food is back in the table. So it is add column, add, and then column name, and then drop, and then column name. The reason we say that we do not want select star from person, why star keyword is bad, is because there are commands like alter table which can modify uh, the columns that are present in the table. And then if that is the case, you would always want to you would always want to define or specify the column name that are present in the system. Okay, at the moment we don't have any data, so it's not going to come back with any query. But then queries like these, they are not going to affect the output of these of select queries, because the table names are specified. And if this fail, probably you will have better error handling and error messaging. Okay, the reason I did not show you constraint at this point, or probably along with create table, is because there are scenarios, there are cases when you cannot apply that constraint right in at the time of table creation, and you should not even do that. And to add constraint at a later point, once again we are going to depend on the alter command, alter table. I'm going to specify person, and this time I'm going to say add constraint. So the syntax of a constraint is that you start with, I'm probably going to have to say add constraint, and then a constraint has a name. So if you want a primary key, you will have to specify that it's a primary key, and then it generally starts with, you generally want to start with a primary key with a constraint name pk indicating primary key, and then you specify person, and then inside the primary key, you mention all the columns that you want as part of primary key. So let's go ahead and execute only, I forgot the key keyword. Right? So you say alter table, the table name, and then you say add constraint, you provide a name for that, and then you select the type of constraint that you want. There are multiple constraints, primary key, foreign key, there are checks that you can add. You specify that, and then you add all the contributing columns to this particular query. Let's put a semicolon and hit F5, and then the command ran successfully. Let's go ahead and see what we have in the table. So exec sp help, and then the table schema is going to, if we scroll down, it's going to say that the primary key is clustered and it is first name. Okay, we can keep adding this thing to the constraint. Probably because this constraint is added, it's not going to it's going to give us some error. But then I would want to add last name to it as well. So if I run this, now it is giving me an error, and run drop constraint, and then run only the selection, and it has dropped the constraint. Now I'm going to add constraint with the same name. I don't need this line here. I can add constraint, and this time I'm going to specify 2 columns to it. And if I execute the SP help, you're going to see that that constraint has been added. There are 2 columns here, first name and last name. So that is what I wanted to show you in the alter table or the data definition language, right? So moving on. So a database discussion, I believe, will be incomplete if we don't talk about the asset properties. Now, asset is an acronym. Each letter stands for another property. A stands for atomicity. C stands for consistency. I stands for isolation. Some people confuse this for integrity. A is for isolation and D is for durability. So let's go ahead and talk about each of these properties in detail. So atomicity is the ability to commit to the entirety of the transaction as it is occurring. So let me pull up a market. So it, when you're transferring money from, say, person A to person B, right? Person A has a current balance of 100 and person B has a balance of 0. So when you want to transfer, say, $10 to this, at the end of this transaction, the new balance of A should be 90 and new balance of B should be 10. And then when a DBMS system is created, or one of the expectation from a DBMS system is when such transfers or such operations are given, if you apply our concept of DML, I am looking at least 2 queries. One is the update query, update say balance equal to 90, where the account holder name is equal to A. But along with this, we'll have to run a second query where balance is going to be 10 and name is going to be B. Now these 2 queries, they have to run together at the same time and both should run to success. If for any reason any of one of these queries is failing, the system should be restored back to their original balance. Make sense? And that is atomicity. It is the responsibility of the DBMS that a transaction which includes multiple update queries, it has to finish to completion. And every query in that thing should succeed. If that doesn't happen, it should roll back. So this is an official terminology, roll back, and then when it is successful, it should commit. So that is atomicity in short. It is important for preventing cases where partial data is available in the system. Okay, and you would probably not want that. Another, okay, moving on to the consistency part. Consistency, it refers to maintaining data integrity constraints. So a transaction should not violate the integrity in the first place of the database. Um, so consistency, we can have multiple check statements on our table, and then say one of the rules that we can define that the balance of any account should never be negative. It should never be less than one. Should be never be less than 0. Such rules they can be enforced in the database management system through multiple check statements. So the way we have this add constraint statement, we can have statements where we can specify the amount, where we can specify the value that a column is supposed to take. So such constraints are part of this consistency, and the database management system is supposed to honor those constraints and those checks, and that is how the system is maintained in consistency. Uh, the next property is isolation. So isolation indicates that when there are there'll be more than there'll be multiple tables in an application. So as you're working on more complex application, bigger applications, isolation indicates that for table number 1, 2, 3, 4, if we are running a query with a join, right, the DBMS system is supposed to act as a boundary. DBMS, DBMS is going to act like a boundary, and it is going to identify which columns are or which tables they are in transaction right now. Using isolation, it is going to create an independent silo of these tables, and it is going to make sure that other tables, while these two tables are being read for some reason, other queries, they are not allowed to modify the data, right? So it creates an isolation, a boundary around these tables, and this way it ensures that the query result that comes back, it is permanent, it is correct, and it does not modify the data halfway through when the query is getting processed. Okay, so that is part of isolation where a DBMS uh, blocks and groups multiple tables together, and it does not let any modification on the outside. It does not necessarily mean that when these two tables are involved, queries that are coming for independent tables that are outside the isolation boundaries that are going to get blocked too, because if this happens, the performance of the system is going to get affected very, very badly. Another thing, there are two type of operations that you can perform. One is read, and the second is write. The read statement is not going to modify these tables. So multiple reads of a system is going to be allowed, and write statements will have to wait when the read finishes. Now, this statement is not entirely true. There will be scenarios when a DBMS system is going to prioritize the write statement over read because it does not want to. So the official terminology, designing terminology for that is starvation. Suppose the read query is going to take 30 seconds, and when these 30 seconds were in progress, we received a write query. And then this write is waiting because the read is not yet finished. And in the meantime, we received another read query and another read query. So it does not mean that the write query will keep waiting for all these read queries to finish. At some point, it is going to schedule this query for execution, and it's going to fetch the read data, and the other queries will have to wait. And as write is happening, all the read queries at the same time and all the other write queries, they will have to keep waiting as well. So this is I'm positive that this is present in databases as well, but this is more of an operating system scheduling concept. But databases do very similar thing under isolation. The last property in ACID is durability, and durability actually indicates that across crashes, across server restarts, when your machine reboots for whatever reason, you would want to persist the data uh, across the lifespan of the data. So when you want to reboot, the data is not going to go away, and the data is saved, persisted on a durable storage like a hard drive. Another concept on these lines is having a backup drive or a fallback drive for these particular systems. So as a write command comes, instead of writing it at one spot, the database, the DBMS ensures, or depending on how you have configured it, it puts that data back on the second category, on the second set of data disk as well. That means in case this disk is to fail, this system comes back up, or this drive is used, and it is going to cater to the upcoming requests or new requests that are coming. All right. So this is asset property for you. Any database management system is going to implement these four properties for you. All these four properties, they must hold together for the type of database that we are studying since yesterday. The relational database, they have very specific requirement of ACID, right? Starting tomorrow, we're going to look at a different type of database system, and it is called NoSQL on, or yeah, I would use NoSQL word. So in NoSQL, the ACID properties, they hold good, but then they don't provide any timeline. So the way we looked at this money transfer requirement, like when $10 is getting transferred from account A to account B, everything related to these two accounts is going to come to a halt until this transaction statement completes. So when this gets to 90, this gets to 10, and the DBMS verifies that both the updates query have ran successfully, that's when this transition is going to complete, and then these tables or rows will be available to the outside system. NoSQL databases, in one of the implementation, they go easy on the consistency part, or the atomicity part. I think I spelled it wrong. It is atomicity. Uh, NoSQL databases, though, they go easy on the atomicity constraint, atomicity part, and then they say that eventually the data is going to get in sync. So once you have given us a request for transferring $10, it is not going to be a financial transaction, but then just for our example, once you have given a request to modify two different tables, it is the responsibility of the DBMS that eventually it is going to have 90 and 10 in each of these things. And I'm going to show you a trick of how to build systems around these conditions. Number one, you don't want to have columns in your database um, that are representing account balance or information like that, because account balance honestly is not a single value. Account balance is a series of values. So when you open your account day one, the balance is zero until you deposit some initial money to it. So you deposit $1,000 in it, so your account balance is going to bump up to $1,000, and then you're going to make some transactions. So if you withdraw $500, your new balance is going to be $500. So tables like these that keep track of the money that you have deposited, the money you have withdrawn, they eventually contribute to the account balance. Now, once you start using account balance as a single value, you lose the ability of identifying what all activities happened inside your account. So account balance still is going to be a number, but then this number is going to be a total sum of all the values, or of all the transactions, deposit and withdrawals on your account. That is going to indicate your account balance. Now, this is going to create a very tricky situation. And then in such cases, you don't want to store just the account balance. Alongside it, you are also going to store the date or the timestamp with that particular um, transaction. So you opened your account on the 1st of June, and then on 2nd of June, you deposited $1,000. On 3rd of June, you deposited another 500. And then when you want to know the balance, you are not only going to say that, hey, give me the account balance for account number A. You are going to say that get balance, and you're going to specify the account, and you're also going to specify the timestamp at, say, 3rd June, 10 a.m. What was the balance of this particular account? And in this way, you will never come with an information which was not current with based on the current input that you are providing. So um, databases or table designing is subject to a lot of such uh, constraints around which these systems have to be built. One such is that you don't want to store account balance as a single number. All right. So NoSQL databases, they are a little easy on one of these four things. Implementing all these four together at the same time is a tricky thing. And depending on what framework you're using, they are going to either compromise or they are going to do it at a later point, and that is going to define or make those databases special. And those databases, they work the best in certain situations. So a newspaper would probably want to use eventual consistency. Just because I saved the news here in India, in Pune here, it does not mean that somewhere in the West, in the US, they would be very interested in those news as well. So if they query that what is happening in Pune, they're going to see probably 2-day old result. But um, when people from Pune, they Google or they search something that what is happening in Pune, they are going to see the current result. And then the topology for that is going to be that this probably system here represents a database in Pune, India, and then this is probably New York. Eventually, after 1 day or 2 day, these two databases are going to come in sync. So these are asset properties for you. Let's move on to the next topic. All right, so we're going to talk about database design, and then the first important concept that you're supposed to understand is what is an entity. So when you when you start working on database or data centric applications, entity, you will be given, say, problem statements. So I had recorded a problem statement for you. Let me go ahead and let me just go ahead and narrate that for you. So uh, there is a there is a sports club, and then that sports club has, excuse me, that sports club has, say, a badminton court, uh, uh, a tennis court, right? And inside these courts, there are multiple of those. There are like 4 courts. Now there's badminton court. They have players, and then these players, they make a reservation online, and they come and play they come and play here at the scheduled time, and they pay the money for that. Now there are multiple courts that are available, and there are multiple people in the system. Now if you if you start looking at these people, if you start looking at people and you think about how you would want to save this information, uh, Dave is a different person than John, right? And then when when Dave calls and says that I want a booking for 8 p.m., it is a different entry than John calling and saying that he wants to booking for court number 1 for 8 p.m. So how do you store this information? And then this leads to a different type of discussion altogether. Then the statement that we read, they're going to sound like members call and book a quote for a time on a specific day, something like this. Now, when you come across such statements, uh, there are keywords that should stand out for you, like a member is present and he's going to book a quote and there's going to be a time. When you start reading these English-like sentences, you will have to you will have to draw mapping between these elements. Like there is a member, then the member is going to have a booking, right? One good way of um, dissecting or understanding these statements is that you start replacing these common sounding names, because the person who is going to give you these requirements, he's going to be he's going to use this kind of language that a member calls and books a code on a specific time, but then you can translate it to Dave called the phone number and requested to book 8 p.m. slot, 10th of June, right? And then this thing is going to indicate that there is a person called Dave, and you would want to store that information when you are when you are building such an application. Now, Dave is a name, and then at this point, you would want to come here and add a property called name. But then they have another condition that to make a booking, you have to be at least, say, 18 years old. Minors cannot call and book codes for themselves. In that case, you will run into a new requirement that minors cannot book in, and then that would give you another indicator that for designing things like this, you will require another column called date of birth. Now, the reason you would put date of birth along with the member field is because date of birth or date can be multiple is present in the system multiple times. So the question that you should ask when you are designing or building databases is if they can be replaced with other values. They can be substituted, they can be replaced, and they occur in the system at multiple times. They become an entity. So um, there could be multiple dates, a date for booking. So a booking is also going to have a date, and a member is also going to have a date. But date in a member represents something different, and date in a booking represents something different. So data types or field like date, they become columns in the table, and then those tables themselves, because they have some association, they become the tables. Uh, One other way of identifying such thing is that you are going to see that word a lot of times. So a member is calling, a member has canceled the booking, a member has paid the membership fees, a member requested a scheduled transfer, a member requested a refund. When you see name of somebody a lot of times or some role appearing multiple times in English sentences, you would understand that they are important, and because they are an important entity of the system, and because they are an important entity, they become a table as well. There are at least four type of information that is going to be presented to you in those English-like sentences. Um, and then those sentences, they are going to help you identify how to build a database or how to build those entities and models. So one is going to be the fact. Second is going to be constraints. Third is going to be examples, and everything else is also going to be there. So let me pull up a requirement that somebody gave for, right. So somebody gave for working a system that is around a sports club. So let's go ahead and start using color codes for all these different types. So we're going to call fact type with orange, constraint with, say, okay, I don't have a red color here. So we're going to put constraint in red. We're going to put examples in blue, and everything else we're going to just leave with a yellow highlighter. Like so, okay, a yellow highlighter. All right, so the first thing that stands out is we have to spot the fact that are present in this statement, in this conversation with a client. So it's going to say during tournament, members, and then they're going to play matches, right? So if you take this 3-line English sentence and if you start dissecting it, it's going to say that during tournaments, members play matches. And then this is going to become our entity relationship diagram. There is going to be an entity over here called a tournament. And this tournament is going to have members over here. And then these members, they are going to share a relationship like so. Then I'm going to say play. So I'm going to put that conceit over here. Make sense? So you will have to read through the lines, and these lines, they are going to tell you more information about which things and then how are they connected. Now, coming to the example part, the example that they have given here is examples generally start with sentences like this, like and such as the 2012 Christmas tournament, right? So 2012 Christmas tournament is an example of the tournaments that we can create. And this is going to give us some idea about how do we want to structure our table. Over here, we're going to say the date. It is probably going to represent something like 2012. And then we're going to have the occasion as well. Probably it's a summer event, probably it's a Christmas time event. And then we can simply call it name. So this is how it is going to become a um, this is how we're going to identify the columns that are supposed to go inside this entity. Okay, now let's look at an example of a constraint over here. We're going to pick up the red marker. The constraint is 3, right? Each member, competing members, they are going to have 3 matches and against different opponents, right? So when you have multiple players, say Dave and John and Mary and Smith, Dave can only play with different members all the time. He cannot keep playing he cannot keep having competition with the same person multiple times. And these are the things that you will have to accommodate for when you are building database systems, right? Then there's going to be a lot of noise as well, which is going to be a detail that you can ignore. Like at the end of the match, the player writes down, right? This is something that you can ignore. But then this looks like reporting. So there is another fact that there is something called as frames. Each player has one, right? And you would want to identify their highest break, all right? And then knowledge of English language at this point is extremely important because this thing here is also a constraint. Notice that the break here is a singular format. So a break is um, a score that you're going to get, and you will have to score you will have to store the highest score that the candidate has made. And that probably is going to give you another table about what happened in those tournaments that you would want to keep track of the games that were played. And then inside those games, you would want to identify what was the highest break, right? So this is the number that we are going to save as we are building the application. So a tournament is going to have multiple games. and then games are going to get played between members. So there's going to be a self-reference, and inside a game you would want to have members as well. And then over here you can define the relationship, like tournament has games and member participates, or I'm going to say compete uh, in the games. This would this would make us want to add a couple of more columns to it, or probably let's table that discussion. But then at this point, I would probably also want to introduce relationships to you. So tournament and members have relationship, but then one tournament can have, excuse me, one tournament can have multiple members. And then when you have um, such constraints that inside one tournament, there can be multiple members, you can specify, this is a UML syntax. This is not a entity framework syntax. Um, I'm so sorry. This is not a entity relationship diagram syntax. In entity relationship, you draw a circle on the parent type. So it is the parent that is containing a tournament. And if it is optional for members to participate in tournament, and they need not necessarily participate in a tournament, you can draw a diamond here indicating an optional thing. So the way it is going to read is that inside one tournament, there can be one or more members, right? So this is a diagramming technique. When you want to say that one tournament can have exactly 10 teams, the way we have in IPL, or 8 teams, you're going to, there are ways in which you can specify. And in that case, it is not going to become uh, a diamond. It is going to become probably a solid line, and you're going to specify the count that it's going to have. So in one tournament IPL, there will be at least 8 teams, or exactly 8 teams. If you want to be a little more flexible here, you can specify a range as well, like at least 2 teams should participate or maximum 8 teams should be there. If you have more, okay, so not the parentheses, if you have more specific conditions that how many members can participate, you can provide a footnote like text here, and then all the English that you would want to provide around this, they can be mentioned here. These AR diagrams, they are for database developers, and based on these diagrams, they are going to go and write those create and DDL queries, using which this is going to this schema is going to become formal in the database management system, right? So based on what we have discussed here, uh, a good structure is going to, a good tournament scorecard is going to look something like this. And we have the match itself, we have the results, and then we have the highest break. And then because we had a player Dave, he played in 3 matches and his highest score was 28, for example. There was another player Zia, he played no matches and then he had a break of 9. Okay, because the results and the tournament itself was optional. I did not participate, and then my break was 9. Okay, so through these diagramming techniques, the information is going to come out like this in this format. Right? It's 9 o'clock. Let's take a quick break and then we're going to come back in 10 minutes. Right? Thank you. All right, guys, I am back. Who has joined using Skype? I see somebody named Live CID. Can you please unmute yourself and tell me? All right, so let's get started. So when we left, we were looking at English-like sentences. We were looking at entities. We made a few points about how to identify entities. A few subtle clues are that they appear multiple times in the system, and they cannot be replaced. Uh, uh, Columns like date, values like date, they can be replaced and interchanged. When something can be interchanged, it becomes generally an attribute. Uh, then we looked at a long English-like statement, and then this statement indicates the general term for that is mission statement as to what you want to achieve from that system. And inside mission statements, using these four type of criterias, you can identify uh, the fact and the constraint and the examples of the system, and you can build that system around it. Um, Another thing that I want to tell you at this point is that uh, databases, they do not store values, they store facts. And that leads to a very interesting discussion that if I have a table called member and member has a field called Dave and John and Mary, uh, they can have different values. They can have, say, a favorite color or a hair. So somebody has favorite color red, somebody has blue, somebody has green. Uh, the way we would want to store this information greatly influences um, the choice of how we would want to divide this particular record. So say Dave likes red and John likes blue. There will be definitely other people who would probably also like the same color. So I might like a red color myself. And then the question at this point is, does repeating information over here is doing any form of violation? So this is one question that I would want you to keep in mind right now. And then let's try to build something on the similar lines that this is Dave, the phone number is 555-1234. And then his email address is dave@d.com. And probably uh, he has a booking for, say, 10th of June. All right. We can have another record for John, and his number is 555 and then 7896. And then it is the email ID. And he has another booking on 11th of June. Okay. The question is, does it make sense to store information of Dave, his phone number, and the booking details, everything in the same column? And the way to judge this is um, what information belongs at what particular spot. We'll have to specify that. Otherwise, when Dave calls in and says that he has a change of plan and he doesn't want to play on this particular date, which is fine. People, one of the requirements that was given was members can cancel their bookings. So with that booking gone, we have we have made the adjustment. The code is now free and available for other people, but then we have also lost Dave's phone number. And then this should be your clue number one about how you would want to divide data and how you would want to separate them into their own silos and boxes where this information makes sense. So if we were to devise a system which is about taking bookings, we would we want to have some logical partitioning as to what information belongs in what table. So a member table should store the phone number, the email ID, and That's it. And the bookings table should have the booking ID, the code, and the date or time at which the slot is booked for. And then if a member is allowed to make booking, they should they should share. One member can have multiple bookings. So I'm going to put a 1 here and I'm going to put n here. It is a one-to-many relationship. One member can have many bookings. And then through this, we are going to keep track of the information. But then this is not it. Um, John can have multiple phone numbers here, right? And if that happens, what are you going to do about that? You're going to say put phone 1, phone 2, phone 3. And then this becomes another type of issue that you would want to address as you are working on identifying entities and defining databases. Uh, okay, the way we would solve this problem is we are going to identify the type of information that we want saved. If a person named John is allowed to have, say, 3 phone numbers, or if anybody in the system is maximum allowed to have 3 phone numbers, it is okay to save these things as separate columns. If he can have 2 emails, we can save that as comma separated values. But then there'll be no constraint, no check on this thing that we can apply very easily. And then at this point, it is probably a good idea to divide this table into multiple separate tables and columns, one for member. And then if you just want to have email and then you want to allow as many emails as they want, you can keep storing, you can go and store those email values over here. And then you build a relationship between the member and their email table. So it is going to be almost the same for um, phone numbers as well, and then you can have as many phone numbers as you want. If that is one of the system requirement, you can go ahead and start dividing those tables into separate columns of their own. The only question that you have to ask is that does this information belong here, and then is this information going to get extended beyond that particular one column. If you want to have better control over the type of information that you want to save, you will have to pull them out and make them part of their own separate column. Okay, question is, does the red here make the information redundant? And then the way I'm going to answer that is I'm going to say no, because databases they're about fact. So Dave likes red color and Zia likes red color too. Okay, so as long as one row is representing one fact, you are not doing any kind of repetition. Because if we go ahead and start applying these concepts the way we separated phone number and email, our this data structure is going to look a little different. And this time around, we're going to say that, you know what, we're not going to save this information. We are just going to save their code, then their references here, and then those references, they are going to point to some solid data somewhere else. So there will be a table called colors, and 1 is for red, and 2 is for green, and 3 is for blue, right? If this is duplicate, red and red, even 1 and 1 are duplicate. So the way data division is going to happen as you are building multiple entities, that is a very tricky concept. And it all depends on how you want to use data. So this is the central question that is going to specify everything. Um, let's look at another view of this table member. And the first column I'm going to say is first name, or let me call it full name. And then the next column I'm going to call address. And then the next column I'm going to call is phone number. Okay. Now, if I start populating this value, it is Dave Smith, and address is 1 Main Street, and then zip code, and then a phone number at the end over here. All right. Now the question is first name a good division, or we should be storing the name as um, first name and last name, and address as, say, the area code, the street name, the zip code as 4 different columns. And then it all depends on this question that we are putting here: how to use data. If we are going to print this thing on an envelope here, right? There is a stamp here. This is my address. And then over here, I'm going to put Dave's address, Dave Smith, 1 Main Street with this zip code. And then this is the phone number if you want to contact. If this is the objective of this particular table, then I am okay with having full name as the column in this thing. But then it's going to get tricky when you say that, you know what, this envelope is going to have a letter inside it, and then that letter is going to start with the sentence, "Dear Dave," something like this, right? If the letter is going to start like this, then probably storing full name like this is not going to help, because at some level we'll have to apply some select function, and those select function, they are going to extract out the first piece of the full name column. And then when so this thing once again uh, once again says that our database at the moment is not enough, is not appropriate. We are being forced to use multiple operations, multiple functions in the select query. We don't want that. So you would want to create a new member table, and this is where probably you're going to use the alter query. And inside this alter query, it is going to say um, first name, and you're going to save Dave here. And probably you can keep working here, call it last name, and inside the last name, you would go ahead and provide the last name here as Smith, right? But then uh, this is fine. But then what if for some reason you don't want to use the full name? You would want to, because of, say, psychiatrists have this specific requirement that they are not allowed to use initials. They are not allowed to use first name. They are only allowed to use initials. So they are going to create a different member table, and then it is called, the first name is called first name initial, and then they're going to save D here, just a D, and then some, they probably will store first name somewhere else, but then the first name itself is going to look like this. And when they want to create a report of their analysis, they would probably use the initial, that this report is for D, then the parameters and the values, the parameters and the values, stuff like this. So once again, the case that we are trying to make is that there is a question. It is called how your data is going to be used. If the data is going to get used in a specific format at a specific spot, uh, a particular schema of table is going to be fine. But then if there are specific requirements that you would want first name and last name separated, you're going to put them in separate columns. And then depending on how your data is coming in picture, uh, is getting used, you would want to further divide first name into, say, first name initial and first name itself. Make sense? So this is about so these are like little tricky questions about how you would identify those columns and tables inside your system. And then this is the question that you should keep in mind. So that brings to our last topic for today, and it is called normalization. So a normalization is identifying what um, is taking a table and applying database designing rules to it. And those rules are called normalization rules. Now, there are multiple normalizations possible. Um, the value of that is OK. So they have multiple names. It is first normal form, second normal form, third normal form, and then it goes all the way up to, I guess, the sixth normal form. For today, I'm going to explain first normal form and second normal form, and I'm going to attempt to explain the third normal form as well. But then all the other normal forms, um, they're something that I would encourage you to study by yourself. And the opposite of normalization is called as denormalization. So we're going to end our session with a quick discussion on denormalization, and we have not used it, but we have already seen it in the output of sp help command. So I'm going to point you to that as well. So let's start with the first normal form. The first normal form says that each table should have a primary key. So if I can pick this up and I can paste it here, all it is saying that there has to be a primary key available inside this particular table, right? And then the reason of having a primary key is that you would want to separate out these records from the rest of the records. You would want to have individually identify um, these columns and these tables. So as long as you have a primary key, you are honoring the first normal form, right? The second requirement of first normal form, let me go ahead and put those here. So the first requirement is primary key. The second is that all the attributes, so attributes is a data set theory name for columns. So all the attributes, they should be atomic, right? And atomic is that we are not going to store full name. We are going to divide these columns into a column of themselves. So it's going to become first name and last name, and probably address column is also going to become a column of its own, like multiple column of its own. So it's going to become, say, the street address, and then I'm going to say city and zip code. So when you do this, you are first name, first, you are in the first normal form, right? And this is the phone number. So when you make divisions like this, that all the attributes are atomic as well, then that is the first normal form. So this one is pretty straightforward. The second normal form is a little tricky. So let me go ahead and put that here. So the second normal form, I'm going to pull up a diagram over here, and let me explain this diagram to you first. So there is an example table, and then the example table says that A here is the primary key. Okay, a primary key indicates that I'm going to have my table is going to have multiple rows in it, like the first row, the second row, the third row, fourth row. And then these four rows, they are going to have at least 5 different values in it. Value B, value C, value D, E, and F. Using A in the where clause, I can get to any of these values. So this thing here indicates that I can get to B using A, I can get to C using A, D, E, and F using A value. So my select query select B from example table where key equal to A is going to give me the only exact value of B which is associated with this particular ID. And that's what makes it the primary key. This table has two more terms mentioned here. Now, when you mention something like this, they become the alternate key of the system. Using B as well, it is possible for you to identify each row of this particular system. So when you can identify rows based on non-key members, that is a representation that is defined here. That using B, you can get to E. So B and E, they have a close connection. So if you say select E from example where key equal to B, it is going to get you the value of E, and it is always going to be unique because B and E share one-to-one relation. That's how it is for DNF. And there are a combination of keys using. So we have seen first name and last name combination earlier, and then if I provide where key 1 equal to B and key 2 equal to C, then I can get to A, D, and F. Now this is creating a complex chart in front of us, and all second normal form says is that if you can get to a if you can get to an attribute, all right, which is not part of your primary key set or this key set, then that has to be separated out. And the way to separate that out is that we are going to pull out the value of E from here. We're going to say remove it. And we're going to create a new column. I'm so sorry. We're going to create a new table. This table is going to be, I'm going to call it fixing second normal form. And it is only going to have one value, which is E over here. And then this E will require a primary key and B becomes a primary key in this case. Now we'll have to establish a relationship between these two tables. And then definitely it is going to be, this is going to be the parent. So a circle here, and it can have one or more optional pointings. So this is going to be a one-to-many relationship. So for multiple values of B, we can have multiple entries inside this table. So this is the second normal form. The third normal form is a close cousin, and it works almost on the similar lines. So this is the third normal form. And the third normal form says that, okay, so I think I forgot telling you one thing, that when you are in the second normal form, it is definitely honoring the first normal form. So one of the condition to get to second normal form is that you are honoring these two conditions of first normal form, that there's a primary key and all the attributes are atomic. Once you do that, you start identifying mappings from what table you can get to what table, right? And inside this one, we have, so what made B special in the second normal form is that it was part of the secondary key value. Using a combination of B and C, you can get to multiple individual values of this particular thing. So B was involved in identifying almost all the members, either directly or indirectly, because it was part of this particular topology. Once we fixed that, once we fixed E out of the equation, we got to the second normal form. The third normal form says that third normal form does everything that the second normal form does. So once this is fixed, we can move on to fixing the third normal form. And over here, we have to identify elements like D and F, right? So D is not primary, but then D can point to unique values of F. So if I say select F from example table where key equal to D, it is always going to come back with one result and it is going to give me one F. And what it says is that you don't allow such entries as well. So we're going to remove F as well. And inside F, we are going to once again apply the same theory. We're going to create another column, another table with, I'm so sorry, with D being the primary key and F being the value. And we establish the same relationship over here of one to many. All right, and that is the third normal form. So in the third normal form, members that are not even a primary key, either in a composite or in the primary key itself, we identify those relationships and we pull those relationships out and we pull them into a table of themselves, and then we assign a relationship between these tables. The fourth normal form, the fifth normal form, they are combination, they are multiple, going deeper on these lines, and then they try to generate graph like this, and they identify these relationships. Okay, if you are interested, you can write a JavaScript program that is going to create that is going to take this thing as an input, and it is going to identify the relationships, and it is going to tell you how to fix the second normal form and the third normal form. Right? If you're interested, you can take one such assignment for yourselves. All right, so we started with one table. We fixed the second normal form. We ended up with two tables, and then we fixed the third normal form and we created another table. When we apply these things, we end up with a combination of multiple tables. Now, these tables, they are essential because it is through this kind of database designing that your application's performance improves. With that said, to make a case for denormalization, I'm going to talk about at least two things. So there are two type of uh, tables or databases that are there. One is called the OLTP, online transaction processing, and one is called OLAP, and it is online analytical processing. So the way these two are different is that transactional is more of day-to-day operation. So as you go to Amazon and you start purchasing item, as a user, we're going to have a, a table for yourself, and it is called the order table. It's not going to be specific to one user, but then say user ID one placed an item order for item number one, and then he made a payment of $500, and the shipping address is something. Such transactions are what is happening inside Amazon.com, like at a massive rate. You are a customer over here, right? There are other combination, there are other entries that are also happening from the vendor side. So vendors are constantly adding and removing elements and products into the system. So this is priced at 500, and there are say 100 items available in the stock. So vendors are also contributing to the Amazon's database, and this is transactional database. As we interact with Amazon.com, this quantity sometimes goes up, sometimes goes down. This order information that gets added, you keep buying products, you keep buying stuff, and then there are more and more entries that get added to these transaction table. This is one type of system. The other type of system is the analytical system. So yesterday we looked at multiple questions like tell me how many members we have. Tell me what is the name of my first member. Tell me how many stocks are available in the car. Tell me which people are interested in what type of car. When you run into those type of query, what you are actually doing where you would want to combine information is you would not want to divide these databases into these tables into multiple smaller table that are interlinked, because when you take join from the example yesterday, the people table had about 1000 rows and the cars table had about 1000 rows. When we took our first join, the cross join Cartesian join, we ended up with 1 million rows, and that was kind of slowing us down. So we switched to the left outer join, and in the left outer join, the processing was fast, and we came back with about 5,300, 400 odd rows. So joining two tables is a time consuming operation, and you would want to avoid taking multiple joins all the time. And for that, databases, they have a provision called creating views. So if I can pull up the SQL Server once again, and let me go back to this stored procedure. I'm going to call execute sp underscore help. If I hit F5 now, let me increase the result window. Notice that there is something called as view. Okay. So these views, they are the exact opposite of normalization. Now, these views, when you query these views, they are going to come back with a lot of data. And then this data is generally a join query or something that the database administrator has identified about the system itself. Like uh, you would want to identify table information multiple times. You would want to do some analytics on the order and the vendor, like which vendor is contributing to the maximum orders in our system. So if that is the question that Amazon is asking, a join of these two tables is going to come in handy. But then you don't want to run the join query every time. So you are going to come here and you're going to create something called as view inside Visual Studio. There is an object that you can create, and this object is going to make a retrieval of similar information easy in the future. The way it is going to be faster is because SQL Server takes up these queries, and then probably queries like the insert or other queries that we saw yesterday, and then it compiles them, and pre-compiled queries, they execute faster. So views is database's way of running things faster in the background. So that is views. One distinction that probably I should make at this point is that uh, normalization is the technique of dividing single column, single table into multiple tables so that your data is better organized and they are sharing relationship and easier to maintain. Denormalize is putting together the tables that you had separated once again together so that you can perform analysis on them. But then it does not indicate that this data is unnormalized. This is unnormalized data where we did not have primary key. So if I scroll back up, this here is unnormalized data. We had no processing done on the type of column we want, the type of tables we want. Using normalization, we came up with a more efficient way of dividing this data and storing this data. Denormalization happens after you have done normalization. So is it okay to call it opposite of normalization? I would say no. After you have done your normalization exercise, like 1, 2, 3, 4, 5, 6, all the way down, then you start coming back and then you start rolling these things together so that your analysis work becomes a little faster. Okay, so unnormalized data, you start here, you go to normalization, you apply your normalization, and then you, through join queries, you come back with different views, and those views are denormalized. There are multiple techniques that are there for denormalization. One is called snowflake. So one is called the snowflake schema. If I have to show it to you, I'll 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 draw a block like this, and probably I'm going to put sales in the center. And then this sales is not going to be something very straightforward. It is going to be millions of rows. And then these rows, they are connected to different, say, contact or say vendors or say customers. So customers like us, when we are contributing to sale, this database is going to get processed. And then this diagram eventually starts looking like a star. So all the connected tables and views, they sit here, view 1, view 2, and then it starts taking shape of a snowflake or this thing. Another technique of that is called OLAP cubes. Right? And these OLAP cubes are something that is called, the industry name is business intelligence. So if you have ever seen Power BI or BI, if you have heard the word, it is actually a denormalization's specialization or the next step of denormalization where you start applying business intelligence. All right, so with that, we come to the end of the relational database section. If you guys have any question, you can ask it now.